Hello, everybody. ODE revision. When I became a tutor at Merton 10 years ago, I was told that according to some original apocryphal source, our principle in how we did our teaching was roughly this, that in Michaelmas and in Hilary term, we taught you physics, and in Trinity, we taught you how to pass exams. So this applies to mathematics as well, of course. So I guess we are at this point where the fact that you have to pass these exams has to be faced by all of us. What I'm going to try to do today is go through some very basic examples that hopefully will help you pass exams. I apologize in advance to all those of you who came here thinking it was going to be entertaining. It's going to be really, really boring. But you know, needs must. I'm very much against either us or any of you worrying about this exam business until now. But at this point, you kind of have to demonstrate to yourselves, to us, and to the world that you can win in this particular rat race as well as anyone else can, right? So there, it's a slightly different exercise than learning physics, but it's an exercise in overcoming obstacles, which is also a useful thing. Although I should say that we've been asked to comment on feedback that we receive. So I should say that I think there is one person in this audience, I don't know whether they're actually in this audience, who will be very pleased with what I'm about to do. So this was there was a piece of quotable feedback which I now quote to everyone. When a student was terribly upset at me for playing this trick with minimal problem sets and supplementary problem sets and extracurricular problem sets, and what that student was upset about. It had nothing to do with them not realizing that they didn't have to do the supplementary ones or the extracurricular ones. What they were upset about is that those supplementary ones and extracurricular ones were there. Because, and on some level, there is some logic to saying, if you want to dumb down the course, don't tell me that it's being dumbed down. This is one piece of feedback that I'm going to ignore. I will take into account everything else. After all, this is Oxford, and we have to set standards not just for ourselves, but grandly for the world, right? And so the responsibility is great. Yours more than mine, in fact, right? You know, I'm just a passing lectures. You are the actual product of the system. Well, anyway, so let's deal with what the system asks of us. So let me first talk about methods of integration of ODEs, obviously. The sad truth is that in order to be able to do well in ODEs, you have to also do well in calculus, which means you have to be able to integrate. So let's talk about methods of integration of ODEs. So here's a kind of a quintessential example, right? So this is the first example of today. I will post these notes later on, but do take notes now. So let's say we want to solve a Cauchy problem, meaning an initial value problem. Y prime equals to y squared, y of 0 is 1, y at 0 is 1. Well, I suppose it's revealing that if we depart from Newtonian notation and go to Leibniz's one, a derivative is just the ratio of dx and dy, and when we look at it like this, and it's always useful to write it like this, then you can immediately see in such an example that you can distribute variables on two sides of the equal sign. So, so dy over y equals to dx over y squared, sorry, equals to dx, and then literally we integrate. When we integrate on this side, we get x plus a constant, and on this side we get minus 1 over y, and so from that y is equal to minus 1 over x plus c. Now we enforce the boundary condition. There is only one boundary condition because the equation is first order. So y of 0 is minus 1 over c, and that's supposed to be 1. And so c is minus 1. And so y is 1 over 1 minus x, which is a quintessential blow-up picture, right? So this is the behavior. So it blows up at 1, and it starts at 1 here. This is 0, this is x, this is y. So we've solved the equation. Now, you might look at it and realize that actually we haven't found all the solutions. Y equals to 0 is also a solution of that equation. Just this curve. But we need, in this particular case, we needn't worry about it's 0, obviously, because the right-hand side is 0, and the d0 by dx is 0. Right? So that is a solution, but we don't need to worry about it in this case because it's an initial value problem, and y equals to 0 clearly does not satisfy y of 0 equals to 1. Right? So I could turn this point around and say, what if you were asked to solve that equation with the initial condition y of 0 equals to 0? Right? At that point, you would have to realize that you don't need to integrate like this. All you need to do is point out that y remaining 0 is a solution. Okay? So, this can be complicated slightly. To illustrate another point, that it's not always quite as straightforward as this, that there is something that depends only on y on the right-hand side. We can have a situation where there are both types of variables on both sides. So, for example, y prime equals to xy squared. The method, of course, is exactly the same. This again is a case where variables can be distributed between two sides. So it's dy over y squared equals now to x dx, and again we integrate, and this is x squared over 2 plus c, and this is minus 1 over y. And so by the same method, y is equal to 1 over 1 minus x squared over 2. So equations like this is kind of the most obvious version of equations that are called separable. Fundamentally, when you're explicitly solving ordinary differential equations, your task is to take whatever you've got there and turn it into a separable equation. Right? Sometimes it's sort of separable immediately, like in example 1. Sometimes you have to do some trivial operation like moving variables from one side to another to make it separable, like in example 2. Let's do another example, which is going to be somewhat more complicated and maybe less obvious in terms of how to handle on various stages. So let's do this and still ask for the same initial condition. So this equation is not obviously separable. you can't simply redistribute variables, but it's quite clear that this combination is begging to be called Z, right? And so we grant its wish to be called Z and realize that this new function accomplishes the turning of the equation into a separable one, right? So let's call that Z, and let's check whether that's true. So let's see what Z prime is. Z prime is 4 plus 2y prime, which means that y prime is half Z prime minus 2. So what this accomplishes is that, I'm about to substitute this into the left-hand side, and this will leave me with just Z prime in the left-hand side, and in the right-hand side I now only have square root of Z. So the equation is about to become separable. The reason this works is because this combination in which x and y are entangled in a non-separable way is linear in x. So when you differentiate it here, right, x disappears. Right? That's a kind of a key insight here. So let's see what will happen. Let's take this thing and substitute it in there. In principle, I could at this point say, fine, it's obvious from this point on. But I want to do the integral because sometimes one also has to think while doing the integrals. So half Z prime minus 2 equals to square root of Z, right? That's what our equation has become. Or Z prime equals to 2 square root of Z plus 4. So it is indeed separable. This is dz over 2 square root of, gosh, this chalk is absolutely terrible. So 2 square root of Z over 4 plus 4 equals to, on the other side, simply just dx. And now we have to integrate these things. Well, integrating this is easy. Integrating this, well, this combination here is now begging to be called u, clearly, right? So u is square root of z. Let's do it like this, and turn this into. So this is dz, and z is u squared, so it's du squared divided by 2u plus 4, and that's 2u du, 2u plus 4. So 2 nicely cancels. And now, so this now becomes u plus 2. And here on top we have u, so we add and subtract 2. And that gives us u plus 2 minus 2 divided by u plus 2 du. That gives us 1, and so it's u, and this gives us minus 2 divided by u plus 2. That's a log. Minus 2 log u plus 2. Now, the crucial step now, not to screw up, is to reassemble everything back together. So let's see. U was square root of z. So this is square root of z minus 2 log square root of z plus 2. And z was that thing under the square root. So this is 4x plus 2y minus 1 minus 2 log 2 plus square root of 4x plus 2y minus 1. And finally, never forget, if initial condition is given, it has to be respected. So in order to make, so y of 0 equals to 1. So this is, let's see, so this equation, which is this equals to x plus c, we have to substitute x equals to 0. And that gives us 2 minus 1 here, so this is 1, minus 2 log, so here we have 0, and 2 times 1 minus 1 is 1, so it's log 3, and on the other side it's c. And so that's the constant. Okay? And so answer. X plus 1 minus 2 log 3 equals 2 square root 4x plus 2y minus 1 minus 2 log 2 plus square root of 4x plus 2y minus 1. Now, when you're writing your exam, always write down the answer at the end and put a box around it or something like that. Okay? Let me give you an insight into the psychology of the examiner. I don't know who the examiner is, so it's psychology of an examiner. So an examiner is sitting there in his or her lonely office with a pile of 200 scripts. Well, on average, it's a pile of 100 scripts on one side, which they have checked, and another 100 scripts which they haven't. They're looking at that unchecked 100, and their sort of prospects for survival are low, right? And their sort of outlook on the world is very dark. So when they're looking at a script where they can't bloody figure out what the answer is, this person is thinking, their level of goodwill towards the person not writing down the answer drops, right? So on the contrary, if there is a neat and correct answer written in a nice box, they say, tick, fantastic, next question. So I am, of course, somewhat trivializing the highly intellectual process that occurs there, but you know, take this on board, right? It's important to be clear in your script about what you have done, and B, it's important to get the right answer. Which incidentally also means that when you're doing the algebra, make sure you do it correctly, which means that's especially a message to those of you who would like to do it quickly. Don't do it as quickly as you would like to, because typically doing algebra extra quickly amounts to having to do it twice. All right. So another thing in sort of within the same kind of set of obvious statements, I suspect those of you with a neat, clear handwriting will have an advantage in these exercises. It's not supposed to be like this, but in practice, because this is looked at by a human eye, and also remember that eye that's looking at it is typically not a 19-year-old eye. So try to be kind to your examiner and give them a clean script with clear logic and answers. Anyway, now these separable ODEs that I have shown you so far are particular and particularly simple cases of equations that are simply in full differentials, right? So at the end of the day, what does it mean to be able to integrate a differential equation? It means you have to be able to reduce it to something like this, right? Generally speaking, right? That's really what we are doing. So generally, this thing could be written as some function of x and y dx plus some other function of x and y dy equals to 0, where this p and this q are derivatives of phi, right? So this is d phi by dx, and this is d phi by dy. And so what we're doing is we're looking at an equation like this, or some version of it, and trying to figure out how do we reverse engineer it back to look like d phi equals to 0. Now, sometimes you're lucky, and what you're looking at is already in this form, in the sense that everything is already a full differential, and that will be true if dp by dy is equal to dp by dx, right? Then tick, right? Then it's dq by dx. So if you see an equation before you and you do a quick check, on the two derivatives like this, and this turns to work, that means that all you need to do is just find the function phi. So here's an example of this. So let's say we write something like this: 2xy dx plus x squared minus y squared dy equals to 0. Okay, let's do d by dy of this. That's 2x. Let's do d by dx of this. That's 2x. And hurrah, right? They are the same. And therefore, the next two lines of algebra that I'm going to write are guaranteed to succeed. So what am I going to say? I'm going to say, well, if this is true, then it must be the case for some function phi that d phi by dx is equal to 2xy. This is a partial with x, so y we are treating as a constant here. Let's integrate this. As I said, treating y as a constant. Well, it's x squared y plus a constant, but constant can be a function of y. Right? Y, if you like, y is a parameter of the equation of this equation. Well, now we have to implement the second bit, which is d phi by dy has to be equal to x squared minus y squared. Well, we already know something about phi, so let's substitute this in there. And this will give us x squared plus c prime of y is equal to x squared minus y squared. X squared conveniently cancels. And so c of y is minus y cubed over 3 plus a constant. So answer, phi is then x squared times y minus y cubed over 3, right? That's why the constant doesn't matter because the equation is d phi of that. But the solution of that equation, d phi equals to 0, is simply this being equal to a constant. I write c for a constant. I don't mean that this c is the same as this c. If you are perturbed by this, give your constants numbers or primes or whatever you like. So there, we've integrated it. Yes, that's fine. So sometimes this effect can be achieved first by multiplying the equation you're given by some integrating factor. Right? So the equation that you start with doesn't always have to nicely satisfy dp by dy equals to dq by dx. Right? That's you know, sometimes you're lucky, but sometimes you have to do an extra step. Incidentally, I wanted to make a comment on this. When you saw here x squared canceling, right? This was have all of you seen The Matrix? There's this movie about how you live in a contrived, computerized universe, right? So, you know, everything looks exactly lifelike, but sometimes these little glitches occur, or little signs of that, you know, that you know, we're all being manipulated, right? I don't know, the cat passes by the door twice or something like that, right? It's, you know, these kinds of things. So when this happens, right, this is a sign, this problem has been contrived by a clever examiner, right? Cancellations have been built into this whole thing. Actually, when you encounter such a sign in doing an exam, that's a very good sign. That means you're doing it right, right? So things start working out. So in a way, your real life is not nearly as nice as this. Although it's surprising how, you know, the elegance of the laws of physics sometimes plays that role. But because we all know we do live in a matrix, right? But you here live in a matrix within a matrix, and so this is one sign of that. So take heart when you see something nicely canceling. And you know, if the answer is very, very ugly, you may have screwed up the algebra. So anyway, so let me show you how this matrix within a matrix is constructed. So suppose I were an examiner and I wanted to give you a thing like this, and somewhere in my checklist of the things that I need to challenge you with in the exam would be use of integrating factor, right? So, and I would look at this and say, that's too simple, right? So, so let me make it slightly more complicated. Let me take this equation. I'm now reverse engineering it back into what might look like a good exam problem. Let me multiply it by 1 over x, right? So if I do that, I get 2y dx plus x minus y squared over x dy equals to 0. And I'll give you this in your exam, right? And so now it looks wonderfully non-trivial, and you get extra points for figuring out that actually if you multiplied it by x, then you would get you would get it into a fully differential form. Now you might be wondering, you know, how to do this systematically, because you know some of you will look at this and say, oh yeah, obviously multiply by x and then this becomes full differentials, right? But that requires a kind of a bit of a sort of a chess master's, you know, two moves ahead kind of thinking. Not everybody thinks like that. So let's see whether we can do this systematically. So systematically, the name of the game is to first suspect that there might be an integrating factor, and then saying, well, let me figure out what that integrating factor is. Let me say that it's, usually it's easier to think of it as a function of only x or only y. It doesn't have to be. This doesn't have to succeed, but that's worth a bet, or worth a try at any rate. So I multiply this by some function mu of x, right? So I look at this equation and say, let's see what can I do, right? So let me multiply it by some function mu. So this becomes 2y mu dx plus x minus y squared over x times mu dy equals to 0. And now I want the d by dy of that, which is 2 mu, and the d by dx of this, which is, what is it? It's mu 1 plus y squared over x squared plus x minus y squared over x times mu prime. So I want these two things to be equal to each other. So I want to find such a mu that this is true. Let's see if I can. So let's see, 2 mu, so let me write this carefully. 2 mu equals 2 mu plus mu y squared over x squared plus x mu prime minus y squared over x mu prime. Mu and 2 here cancel. I move this to the left-hand side, and what do I find? Mu 1 minus y squared over x squared. And on this side, I have mu prime times x 1 minus y squared over x squared. X squared because I scaled out x. Aha. So x mu prime equals to mu, and indeed mu equals to x works. Right? Now, generally speaking, solving an equation like this, so just to repeat, mu equals to x works, so if I go back to that equation, multiply it by x, I will get back to the previous equation. Right? So now, typically equations like this are not equations for integrating factors, are not typical. They're not necessarily easier to solve than the original differential equation. But sometimes they are, and your task in this situation is simplified by the fact that you only need a solution. Right? You don't need general solution for the integrating factor. If you find anything at all that works as an integrating factor, that works. Right? So you don't have to worry about constants and what happens if 1 minus y squared over x squared is 0 and therefore cannot be cancelled and stuff like that. right? So none of these concerns apply. Now, interestingly, let me construct another example out of this same example, actually. Let's look at this equation before we multiplied it by mu. Actually, it ended up now being in a particular form that makes it solvable by a different method as well. So let me rearrange dy and dx in the following way. Let me rewrite this equation as dy by dx equals to the right-hand side, which will be minus 2y divided by x minus y squared over x. Right? So all I've done is I left dy in the left-hand side, I moved dx to the right-hand side, and I divided through by the coefficient in front of dy. Okay? So this actually now looks, so now let me divide through by y, the top and the bottom of this fraction. So this becomes minus 2 over x over y minus y over x. Does this strike you as an equation in a familiar form? What's this called? Homogeneous. That's right. So this is called a homogeneous equation. Sorry, it's an equation in the form where dy by dx is equal to f of y over x. Why is it called homogeneous? It's scale invariant, exactly. It's an equation in which I can scale y and x by the same constant and nothing will change. This is actually one of the several types of homogeneity. So this particular homogeneity is invariance with respect to this transformation, right, for any lambda. But actually, there is a more general form of homogeneity where you have an invariance to transformation with respect to here lambda to some power alpha, here lambda to some power beta, and it turns out that identifying such homogeneity in equations almost certainly leads you to some method for solving them. Okay, and I've mentioned a couple of those in my lectures, and also in those infamous supplementary problem sets. You had an example of generalized homogeneity, which you can work through, and it tells you actually within the problem set how to solve equations where these are more generic. So whether such a thing can turn up in an exam, I don't know. Probably not. But yeah. So let's see. So how do we solve this? So again, right? We solve this by what the equation obviously wants us to do, right? And what does the equation want us to do? It wants us to call this z, right? Y over x. So let's obey our own algebra and call z equals to y over x, or equivalently, y equals to x z of x. If that's the case, if we do that, then y prime is z plus x z prime. And let's try to solve our equation yet again, right? So z plus x z prime equals to minus 2 over, and now since z is y over x, this is 1 over z minus z. That's the equation we're trying to solve. Okay, well, x z prime is equal to 2 z minus 1 over z minus z. If you, well, let's do this. So this is, first of all, so I multiply by z on both sides, 2z, z squared minus 1 minus z equals to, Okay, so it's 2z minus z cube plus z divided by z squared minus 1. And so this is minus z times z squared minus 3 divided by z squared minus 1. Okay, so that's what we need to integrate. And it's xz prime equals to that. So again, we redistribute variables. So we get dz. This goes into the left-hand side. So this becomes z squared minus 1 divided by z squared minus 3 equals to minus. And here we have x and dx on the bottom. So this is dx over x, like that. And we integrate. This is easy on this side, but on the left-hand side, we have to work a little. So, what do we do? Well, we split the product on the bottom, right? So you have to turn this into fractions. So this expression, I want it to look as a over z plus bz plus c divided by z squared minus 3. Right? So I want it to look like that, and then by requiring that it looks like this, I can now figure out what a, b, and c are. Well, so this is a z squared minus 3a plus bz squared plus cz divided by z squared minus 3, and now I have to match this to that, right? From which I learned that c must be 0, a plus b must be 1, because that's the coefficient in front of z squared, and a is 1/3, minus, yes, 1/3, because minus 3a has to be equal to minus 1. And so from this then, b is 2/3. And so our equation becomes c minus log x. This c is different than that c, obviously. I'm sorry about this. You can call, let's call this c1. So that's equal to, so we now are integrating this expression with these constants. So the first one is just, so it's 1/3 dz over z plus 2/3 z dz over z squared minus 3. This here is log z. And this here, well, 1/3 log z. And this here is 1/3. And notice that 2 times z times dz is dz squared. And we have z squared on the bottom. So this is log of z squared minus 3. Right. So let's now assemble everything. So this here is constant divided by x. So I'm now going to exponentiate all this because there is a log here, and log here. Different constants, so let's call it C2. Equals to z times z squared minus 3, everything to the 1/3 power. Well, this is, let's raise all this to the third power. Then this will become a different constant divided by x cubed equals to z squared minus 3. Now let's restore what z was. Z was y over x. So this is y over x. Y squared over x squared minus 3. Let's multiply through by x cubed. So this constant is going to be equal to y cubed minus 3x squared y, or equivalently x squared y minus y cubed over 3 is equal to, I divide through by 3 and redefine the constant again, and that's C4. And we're back to, where is it? Up there, right? Phi equals to x squared y minus y cubed of 3 equals to a constant. So we've recovered the solution by a different method. This, of course, is a much longer method for recovering it. So that tells you that, you know, things are doable in more than one way, and you know, those who see a quicker way get an advantage in the race. So, but it's good to know many methods of doing this. Well, so just like in the case of separable equations, the fact that an equation is homogeneous can be hidden behind the change of variables. Okay, so so a particularly simple case is one where the change of variables required is linear. So let's consider this. So an example like that. Now, when you look at this, you could see that everything would be great except for this 2 and this 4 here. Right? Because if there wasn't a 2 and a 4, this would be a homogeneous equation. Right? So let's see if we can turn it into a homogeneous equation. Well, let's see, just a sec. Yes, so let's turn it into a homogeneous equation then. So how do we do this? This is so these expressions are linear. So let's try a simple linear change of variables in the following form, right? Let's say that x is now going to be x naught plus xc, and y is going to be y naught plus eta. And the name of the game is to pick x naught and y naught in such a way that the new equation for xc and eta becomes homogeneous. Okay? So now the beauty of this transformation is that it doesn't change dy by dx. So dy by dx is the same as d eta by dxc. But on the right-hand side, let me substitute everything. So this becomes y naught plus eta plus 2 divided by 2x naught plus 2xc plus y naught plus eta minus 4. And I want to engineer y and x naught such that there are no constants here, that only eta xc and eta here remain. So that means this thing has to be 0. And so y naught is minus 2. And here I want this here to be 0. And y naught is already minus 2. So let's see. So it's 2x naught plus y naught minus 4 equals to 0. Y naught is equal to minus 2. So x naught is 3. So this means that our change of variables was x equals to 3 plus c and y equals to minus 2 plus eta. And our new equation for eta and xc is d eta by dxc equals to eta over 2xc plus eta, or equivalently 1 over 2xc over, actually no, I'll divide through by xc rather than by eta. So eta over xc, 2 plus eta over xc. And this is manifestly homogeneous, right? This is a function of eta over xc. And so we know how to solve it. How do we solve it? We solve it by introducing a new variable. So this here is a new variable. Well, we can't use a Latin letter to rename the Greek ones, so we have to use zeta. I assume you all speak ancient Greek, because, you know, either you learned it at school, or since you arrived to Oxford, you've been speaking it to your mates. So it's either by immersion or by coercion. You must have learned it. Right. So zeta is eta over xi, or equivalently, eta is xi times zeta over xi of xi, and so eta prime is equal to zeta plus xi zeta prime. And that is equal to that, which is zeta over 2 plus zeta. So xi zeta prime is equal to zeta over 2 plus zeta minus zeta. And that's equal to zeta minus 2 zeta minus zeta squared divided by 2 plus zeta. And that's equal to minus zeta squared plus zeta divided by zeta plus 2, and that's minus zeta plus 1 over zeta plus 2. So if you get into the stride of solving differential equations with Greek notation, the next stage is to try Cyrillic. But that's strictly extracurricular. Right. Okay. So for once, actually, so clearly what we're about to have to do is to redistribute variables, right? This is now separable, right? Because this here is d zeta by dxc, right? So we're going to pull this into the left-hand side. We're going to pull xi and dxc into the right-hand side and integrate. But for once, let me be careful about dividing by 0, right? Clearly, I can only pull this into the left-hand side if zeta is not 0 and zeta plus 1 is not 0, right? Zeta plus 2 can't be 0 either, because if it were 0, then the whole equation wouldn't be well defined. Right? So that you just have to state, because you know, if you can't be solving a differential equation that's with infinite derivatives, right? So that's it's an assumption that zeta is not equal to minus 2, right? But nobody in principle stopped zeta from being either 0 or minus 1. So let's examine those possibilities first. So zeta equals to 0 actually is a solution of this equation, right? Because when zeta is equal to 0, this is 0, and you know, 0 prime is 0, and so the equation is satisfied. What does zeta equals to 0 mean? Well, it means that zeta, remember, was eta over xi, and eta was y plus 2, and xi was x minus 3. So that's what it means. And so that means y equals to minus 2 is a solution of the equation. And that's a solution additional to the ones that you will recover when you do separation of variables. Right? This could not be recovered that way. There is another one, which is zeta equals to minus 1, right there, right? Well, what does that amount to? Well, that's minus 1 equals to y plus 2 over x minus 3. And if I work out what this is y equals to 1 minus x. This is a solution. Again, a solution that cannot be recovered from the separation of variables. And now, when this is not true, meaning when zeta is not 0 and and not minus 1. What do? Well, we pull the right-hand side into the left-hand side, and etc., and separate variables. So what does that give us? Minus dxc over xc equals to integral zeta plus 2 over zeta plus 1 d zeta. And that is, well, this is quite easy, right? So on this side, sorry, it's log c plus c, and on this side, it's the integral d zeta 2 over zeta minus 1 over zeta plus 1. That's that thing there. And that's just 2 logs, right? So 2 log zeta and minus log of zeta plus 1. And now we start the painstaking process of recovering, of sort of assembling the solution back, right? So this is 2 log eta over xc minus log eta over xc plus 1. So, and that is equal to log eta squared minus 2 log c. And there is another, I'll pull the xc out, so plus log c and minus log of eta plus xc. That's how I wish to write it. Why do I wish to write it like this? Well, because again we realize that we live in a matrix. There is a cancellation, and so I'm only left with this, and the constant, and so eta squared is a constant times eta plus xc. Incidentally, you might be wondering, how is it that I had an absolute value here, and then I got rid of the absolute value? But I can do that because this multiplies a constant, and so both the plus and the minus sign can be absorbed into the constant, right? So we haven't lost anything. Okay, finally, this is y plus 2 squared, this eta, and that's equal to c y plus 2 plus x minus 3, and that's c of y plus x minus 1. So this is a solution in implicit form. In principle, you could resolve it with respect to y, but that's I don't think that's important. Notice that one of the solutions we got earlier, y equals to minus 2, is already here because it corresponds to c equals to 0. Right? So we see that actually we can extend the validity of this solution also to y equals to minus 2. The solution y equals to 1 minus x is not here. So I have to write the solution like this. However, I could have done it differently. So what I could do is I could say c1 is equal to 1 over c and rewrite this as y plus x minus 1 equals to c1 times y plus 2 squared, in which case the solution y equals to 1 minus x is here and corresponds to c1 equals to 2, but I have to specify that y minus 2 is also a solution. So these are 2 ways of writing the full set of integral curves of this equation. So, so these are the main tricks for the one-dimensional equations. The next topic, which I will deal with tomorrow, is a rather big subject of linear equations. And it turns out that while with generic nonlinear equations, we simply just know how to deal with a few special cases. Remember, the majority of ordinary differential equations we cannot solve in quadratures, right? So it's the majority. Even though 100% of the equations in exam scripts can be solved in quadratures, right? This just tells you what a bubble we're living in, right? This sort of all these solvable questions given to us. But it's an important part of it. outside the bubble is overrated anyway, right? Inside the bubble is much nicer life. So, so that's that, and we'll talk about linear equations tomorrow morning. Hand over to you, Professor.
Hello, sir.
Complex analysis?